Today I want to present a solution to Chinese National Olympiad 2020 problem 5. Firstly, we'll take a look at the problem statement. Let P be a convex polyhedron such that an ant can walk on a simple cyclic path S of its edges, where the pair P, S satisfies the two following properties. Firstly, for all vertices V of the polyhedron P, the vertex degree in P of V must be equal to 3. And furthermore, for all positive integers n, the number of n-gons to the left of the ant path is equal to the number of n-gons to the right of the ant path. We need to show that the ant makes equally many left turns and right turns on its cycle around the polyhedron. After being presented with this problem, you might see two main difficulties as to why this problem is not easy. And I want to write them down, first of all. So we have two difficulties. First, it is hard to wrap your head around or to imagine the ant's path in 3D. Okay, so what we see here, for example, we walk around the polyhedron, and on this part of the ant's path, it's on the back of the polyhedron. Therefore, this is a left turn, although from our perspective, where we are looking at it, it doesn't look like a left turn. But of course, you understand that that is still true, but we have to be able to imagine all of this in 3D, which is not easy. And secondly, we don't know much about left and right turns yet, because this is an unfamiliar notion in these types of problems. So before we're going to start with the solution, we need to deal with these difficulties in order to understand how to really solve the problem. The first difficulty can be solved by introducing graphs, which means that we think of the polyhedron P as a graph where its vertices are the vertices of the graph and its edges are again the edges of the new graph. And since P is a polyhedron, its graph is a so-called planar graph, which means we can embed it in a plane without having any two of its edges crossing, and then we can also maintain the notion of faces in this case, which is quite useful. So that's what we're going to do, but furthermore we are going to differentiate P into two graphs, which I call GL and GR. Since our cycle S is non-self-intersecting, it divides P into exactly two regions. And I'm going to consider both of these regions as graphs, where GL consists of all of the vertices on S, or to the left of the end, and all of the edges between two of such edges. And we define GR similarly. Therefore, for example, GL looks something like this when embedded into the plane. So we have our hexagon from the top and four quadrilaterals adjacent to it like this. The boundary of GL in this case is exactly the path S. In this case, GR looks exactly identical to GL. They are both isomorphic, but this is not always the case by definition. Now we are done with dealing with the first difficulty, because we can view P as the sum of two such graphs, which is two-dimensional and a lot easier. Let's continue with difficulty 2. What are left and right turns? To do that step, I want to label all of these vertices which lie on the path S with R and L again by whether or not they were right or left turns originally. So we see that this is a right turn. I'm going to do that quickly. Okay, so now I have labeled all of the vertices with an R or an L, and we can now examine them. And note that I think at this point this is pretty easy to see that all of the vertices labeled with an L are exactly those which are trivial, so they only have two adjacent edges in this graph and not a third one, which basically means we could also remove them. They are just a vertex on an edge. And whereas the vertices are of course vertices with three adjacent edges. This is a pretty useful observation. Now, if we were able to prove that, this would be great because we could use this in our final proof, and on the information of degree of a vertex is very valuable because we know many things about them and how to make deduce other stuff from them. Okay, so now let's take a look at why this might be true. So we're going again to the polyhedron P and look at this left turn. We see that because the end turns left, or rather towards the graph GL, the other option, the path which would have gone to the right, this one right here, is not taken. Because the end turns towards GL, the third edge is omitted from GL, and therefore this vertex must have degree 2. On the other hand, on a vertex with a right turn, we turn away from GL, and therefore the other option, which would have turned towards GL, lies still inside it. So remember that this is all just true because of the condition 1, because in P all vertices must have degree 3. Combined with what we have now observed, we can say that a vertex is a left turn if and only if it has degree 2 in GL, and a vertex is a right turn by symmetry if and only if it has degree 2 in the graph GR. I'm going to note that down on the side and continue with the proof, because we have now found a useful interpretation for left and right turns and can start or continue with our proof. Now we don't have to think about left and right turns, we only have to think about the vertex degrees within the graphs GL and GR. And with that we can finish the problem, but we are not yet there at all. We have to first introduce some notation. So first of all, which is really important, let L be the number of left turns and R be the number of right turns. Furthermore, we introduce the sets VL, EL, and FL, and the sets VR, ER, and FR, which are the sets of vertices, edges, faces of GL and GR respectively. These are quite a lot of new variables, but important ones, because we are motivated to prove that VL, EL, and FL are equal to VR, ER, and FR. Why are we motivated to suspect that? Well, 2 states that the faces of GL and GR have similar properties. And I want to specify what that means. And we hope that these similar properties are enough to show that they are both equal in number of vertices, edges, and faces. Okay, so to do that, we introduce the functions gl of n and cl of n and cr of n, which are the number of faces of gl and gr with n vertices respectively. Okay, respectively, and this is really, these are very nice functions because 2 tells us that for all n in n, cl of n equals cr of n. And this is exactly what I said. We can deduce lots of information about edges, vertices, and faces from that and prove that in the next step. Okay, so take a moment to take in all of these new variables and 2 functions. We're going to prove the next step, that these 2 triples for L and R are equal. So what can we do? For example, we know that the magnitude of the set of FL, so the number of faces in GL, is just nothing but the sum from going from n equals to 1 up to infinity of CL of n. Why is that? CL of n counts the number of faces which are n-sided, and if we sum it up over all possible values of n, we get the total number of faces. But since CL of n equals CR of n, we have this is equal to the sum from n1 to infinity of CR of n, which is nothing but the magnitude of FR. This is a good first step. We can do very similar stuff for EL. It's like similar to the handshaking lemma because we can count all of the edges twice with this sum, the sum going from n equals to 1 to infinity of n times CL of n. Since every face with n sides has also exactly n adjacent edges, and every edge is adjacent to exactly 2 faces, we double count or count this quantity twice by the sum. Therefore, we need to multiply with 1/2, and this equality then is true. And we can do the exact same thing as before. But this is nothing but the magnitude of ER. Very nice. So if you have a little bit of experience with planar graphs, you will know how to finish this. We know that EL and ER are equal in size, and FL and FR are also equal in size. But by Euler's theorem for planar graphs, we also know that VL minus EL plus FL is equal to 2. Where I didn't always say that I'm talking about the magnitude, but it should be clear in this case. And 2 by the same theorem is also equal to VR minus ER plus FR. Okay, so this is really nice. We know that these 2 variables are equal respectively. I'm not going to write out all the algebra, but it is clear that it follows immediately that VL is equal to VR in size. We're going to finish our proof by using the handshaking lemma. We can count twice the number of edges in GL by summing all of its vertex degrees, because every edge is exactly adjacent to 2 vertices. But the sum, okay, I'm going to write this down, V in VL degree VL of V. This inequality holds true by the handshaking lemma, and furthermore we can evaluate this because we know most vertices in VL have degree exactly 3, up to exactly the left turns which have degree exactly 2. So this is equal to twice the number of left turns plus 3 times the magnitude of VL minus L. Now we will rearrange this for the quantity L that we are indeed interested in, and L is equal to 3 times the magnitude of VL minus twice the magnitude of EL. But this is nothing but 3 times the magnitude of VR minus 2 times the magnitude of ER by our previous result. And using the exact same argument for the graph GR, we can obtain this quantity being equal to R. So we know L is equal to R, which finishes our proof.